All I'll discuss in this particular presentation with regard WDM concepts and few components of the wavelength division multiplexing. So first we'll see what is WDM, why it is. The WDM means it is a capacity upgrade of existing fiber network without adding any particular fiber. We are just upgrading a fiber network. The existence of something like transparency and scalability, and also the wavelength routing and switching is also very important with respect to this wavelength division multiplexing. The transparency in the sense each optical channel can carry any transmission format. It might be in terms of different bit rates, or it might be in terms of analog signals or digital signals. The scalability in the factor to buy or install some equipments for additional demand as needed. The wavelength routing and switching is also another dimension to the time and space. So here we can understand the WDM with respect to the different wavelengths, which is passed into the something like multiplexers, so that single fiber line consisting of many wavelengths. So as you can see in the particular diagram, so I'll just point it out. There is W lambda 1, lambda 2, lambda n number of different wavelengths which is passed into, and it is combined using the help of optical multiplexer to make a single line of optical fiber which consisting of all different wavelength signals. So this is how all the wavelength in a single channel which can be transmitted with the help of wavelength division multiplexing. So this is one more diagram which is consisting of many different point or number of loops, multiplexing and demultiplexing unit. As you can see, the input side consisting n number of different wavelengths are multiplexed, put it into the channel with the over a long distance channel which is consisting of many amplifiers, which is consistently used in between, because to amplify intermediate data or whatever the for the long distance, there should be existence of something amplifiers over a long distance. At the receiver side, as you can see, there is existence of demultiplexes. This is mentioned in DMUX to get back all the different wavelengths which is we transmitted, which is receiving back. So passive and active devices are needed to combine, contribute, or distribute, isolate, and amplify optical power at a different wavelengths. This is what the majorly required with respect to the wavelength division multiplexing or WDM. So normally, if I look the WDM, the existence of different versions with respect to the WDM technology, the wavelength division multiplexing consisting different technology, it depends upon the different wavelengths. So how? So as you can see, one part is CWDM, that is what we call it as coarse WDM, has a wider channel spacing 20 nanometer, which is low cost. So for a short distance, which we can make this particular WDM. Another one is dense WDM, that is DWDM, has a dense channel spacing of 0.8 nanometer, which allows many wavelength with the high capacity channel which is considered. So this all this particular the WDM or CWDM or DWDM, everything which is made it by the certain standards. So this standards normally we'll call it as ITUT, that is the International Telecommunication Union. They specify all these particular conditions. So, but the normally the WDM networks just two wavelength, which is normally basically used. The wavelength range from 1310 nanometer to 1550 nanometers. Today, DWDM, that is dense WDM systems, utilizes different wavelengths consisting starting from 16 nanometer to 1550 nanometer window. Till there, it can be used. Each of these wavelength provide an independent channel where the each transmit of 10 GB per second something information. The range of a standardized channel grids includes 50 to 1000 gigahertz spacing. This is what the consisting or conditions. Wavelength spacing partially depends upon the laser line width, also the optical fiber bandwidth. So these are the certain points with regarding the what is the different wavelength can be used with respect to the WDM or DWDM, or with respect to the also in terms of the frequency range over the different channel grids. So this is what I just earlier mentioned about the telecommunication standard, how they defined this with respect to the WDM. But this particular diagram, which is specifically defined for the standard transmission window for DWDM itself. So as you can see, the normally the range what you we can take the 100 gigahertz channel spacing for ITOT standards. The range which we can specify, this range can be 1535 to 1562 nanometers. This is what the wavelength range which is considered with respect to these particular standards. So the first window, second window, or third window, as you can see, this is with the different wavelength, 1300 nanometer range of 1500 nanometer range. That is the third window or second window. These are the windows where the different wavelength can be used for the WDM concept. This is what which we can mention in terms of the graphical representation as per the telecommunication standard. The basic principle with respect to the DWDM, the bandwidth of the modulated laser with respect to 10 to 50 megahertz, or in other way, you can also take it as 0.001 nanometer. Typically, the guard band is zero point 0.4 to 1.6 nanometer. That is the range which is considered with respect to the band with respect to the DWDM. So next is with respect to the 80 nanometer with the different band. This is much important. 80 nanometer or the 120 nanometer with the different ranges of wavelength. Its particular band which is defined with respect to the frequency also. A discrete wavelength form individual channels that can be modulated, routed, and switched individually. These operations require variety of passive and active devices like delta V, which can also be taken in terms of the equation C by lambda square into delta lambda. This is what the conditions which we can take. But normally, with respect to the any WDM standards or any particular conditions which we take, there should be existence of something connections with respect to the different wavelengths. An interferometric device used two interfering paths of different length of to resolve the wavelength. Typically configurations: two 3 dB directional coupler connected with the two paths having different lengths. So interferometer is nothing but it is just kind of a coupler which is having one particular wavelength or the 3 dB directional coupler, which is considered on with respect to one example. So as you can see with respect to this point, 3 dB directional coupler connected with respect to the WDM to connect from one into the two channel or two channel into one channel. This is what how we can make it. The coupling conditions or with respect to one fiber to the another fiber or one to many or many to one. This is how we can do the connections. This is how we can do the multiplexing or multiplexing conditions with the help of interferometer. So applications, as I mentioned, the wideband filters that can be separated from different wavelength are separated with the help of interferometer. The narrowband filters, if I suppose used, if the filter bandwidth they depend on the number of cascades or values which we considered. This is what one basic example to understand the interferometers, which is done by Mach-Zehnder interferometer, and he is the scientist develop this particular one formation of kind of connections with respect to the WDM. So these devices can be active or passive devices, but this usually looks like a passive conditions or passive devices. The existence of phase shift of a propagating wave increases with delta L. As the length increases, the existence of phase shift. the constructive and destructive interference depending upon the again delta L. So as the length changes, the interference of a signal which can be varies further. This we can understand with respect to the example what we considered here. It is 2 cross 2 Mach-Zehnder interferometer consisting the existence of 3 dB splitter and 3 dB combiner, which is used to either to combine or the separator or splitter. So initial 3 dB directional coupler that splits the input signal, a central section where one of the waveguides is longer by delta L to give the wavelength dependent phase shift between the two arms, and another 3 dB coupler at the end to recombine the signal at the output. So what is that? With respect to the one line which is having extra length, that is delta L, another one is having L. So these two are used to the wavelength dependent phase shift between the two arms. So there should be something phase shift which is existed with respect to these two signals. So wavelength is slightly modified with respect to the signals, but this is splitted here, this is combined here, and it is going back further. So this is 2 cross 2 2 cross 2 Mach-Zehnder interferometer. So with the help of this, if suppose the construction as I just mentioned, as per the with respect to the previous diagram, I said the initially 3 dB directional coupler that split the input signals, and then central sections their existence, one of the waveguide is longer given by the wavelength dependent phase shift between the two arms. Another 3 dB coupler is to recombine the signals at the output. The signal then finally emerge out only one output port. That is what the entire explanation with respect to the 2 cross 2 Mach-Zehnder interferometer. But this is very important with respect to the equation point of view. So the phase shift what is observed with respect to the output of the signal is due to the propagation path length difference. The propagation path length difference, that is what we need to understand, how the propagation path length differences, that is we calculated with the help of the equation here is mentioned is a delta phi, which is equal to 2 pi n effective lambda divided by lambda into delta L. In textbook, this delta phi can also be represented as delta V. So that is nothing but delta phi here, which is indicating the frequency of a separation of two wavelengths which is considered, and the value of pi here what we can take in terms of 2 pi n effective, which is 1 by delta lambda 1 minus 1 by lambda 2. This is the variation with respect to the lambda which is expanded in terms of delta L. If the power of the both input to be added at the output port 2, then the equation or value of pi I can get with respect to this equation. And this is the equation which just need to be remembered with respect to the Mach-Zehnder interferometer multiplexes. Especially it is mentioned for 2 cross 2 Mach-Zehnder interferometer. So this is what the example of a 4-channel wavelength multiplexer. Here it is consisting of the 4-channel multiplexers. As you can see, there is 4 input channels with the 4 output channels. So it is a 4 cross 4 example to understand the 4-channel wavelength multiplexers. By approximating here, the selecting delta L, it is different. One is delta L1, delta L2, then delta L3, combining these two combined with the help of this, and these two are combined with the help of delta 2 L2, delta L1, delta L2 combined together to form with the delta L3 to make that. So 4 wavelengths are multiplied and combined together. So this is demultiplexing. We can further we can do it in this again. This stage need to be reversed to the receiver side at the with respect to the Mach-Zehnder